right, so what we want to do here is build cell geometry. So I'm not going to talk about getting in reactions and rates and that sort of thing. I'm going to focus. Yeah. I'm going to focus entirely on how do you build a cell with the tools that we have constructed. So I'm going to remind you guys what the site type lattice is in lattice microbes. It is just a three-dimensional array with a size of the lattice size. So each point in the lattice represents some compartment, some part of a compartment in the cell. And each element of that three-dimensional array is a type of just a byte. So that means that there can be 256 different site types. For practical reasons, you never want to get close to that because like the diffusion matrix is three-dimensional with one of those dimensions being the number of sites. So the site type lattice itself defines the diffusive properties of particles, and it also tells you what kind of reactions are possible. So certain reactions will only happen in certain compartments for whatever reason. So there are two ways to build site type lattices. There's the original way using PyLM, and the way that this works is we have a set of geometric primitives, so like spheres, cubes, cylinders, cones, and you use this to basically design your cell using constructive solid geometry. So you can take a sphere, a cylinder, and another sphere, and take the union of those sets, and you can build a capsule. From the capsule, you can build an E. coli cell or whatever you like.
So I think Mike showed that pretty nicely in his talk.
Yeah, this is more of a practical talk, so I'm going to show you exactly how to do it instead of just kind of giving you an idea of the idea.
Well, he gave the commands. He did a nice job.
Yeah. So with PyLM, once you have constructed the site type, once you've constructed your representation of the geometry in terms of these abstract objects, the code will then project that onto a discrete lattice. So PyLM itself is more well-tested than the methods I showed yesterday, and I will continue to show today, JLM, and there's a lot more geometric primitives available. However, using this sort of technique with constructive solid geometry, once you get towards features that are on the order of lattice spacing, so membranes, pores, filaments, that sort of thing, you lose control of the individual spacing or the individual positioning of sites. And that can lead to trouble later on, especially with membranes. The other method is JLM. And in this case, instead of dealing with these abstract geometric objects, you deal with the site type lattice directly. And what you end up doing is you construct the site type lattice out of a set of binary three-dimensional arrays, which each array defines a region in space. Then you combine them in the end to a site type lattice with a data type of a byte. So this has no explicit discretization, so you have control over the data that actually goes into lattice microbes with a fine level of detail. However, the implementation is new, and I'm pretty much the only person that's been using it, so there are probably corner cases, edge cases, which will break, and I am not aware of them yet. So like please send bug reports.
So Tyler, just looking forward to what you do now with the label-free data, if I understand this correctly, this will allow you more easily, like sort of design even a somewhat irregular shape, say mitochondria, and then you could replicate it, and that would be easier to do with the JLM.
Yes. Yeah,
okay.
You can use more sophisticated generative techniques. In my tutorial, I build cellular obstacles by just generating a set of noise, Gaussian noise, and then taking a threshold. So you can do techniques like that. You can do cellular automata like Jala has done with her HeLa cell. That's a lot easier in JLM. but of course you have to define the actual algorithm.
And those will be part of the afternoon advanced tutorial?
Yes.
Oh, great.
Yep. All right, so forward with PyLM. I'm going to build an E. coli cell. It's going to be 3.6 microns long and 0.8 microns thick. We're going to define an extracellular region, a membrane, cytoplasm, and the nucleoid region where you have a high density of DNA. Membrane is on the order of 4 nanometers in E. coli, so we're just going to have to be okay with a subvolume or a membrane on the order of the cell volume or subvolume size. We're going to say that the nucleoid is half the radius of the cell. So here is an image of what exactly we're going to do here. We have extracellular, we have the membrane region, the cytoplasm, and the nucleoid region. So this is 3.6 microns, and this is 0.8 microns. So this length here, which goes from the centroids of these two spheres, is going to be the length of the cell minus 2 times the radius. So here are our standard imports for PyLM. We bring in the SWIG module, and from the SWIG module we have all of the geometric primitives available. And we bring in the PyLM, RDME simulation, the units that I think Mike showed, and a visualization tool in PyLM. So we start off with a simulation volume with an RDME simulation, and with these, with this definition here, we tell it the size of the subvolumes. We say the dimensions of the lattice in continuous units, not subvolume units. We give it the simulation an identifier, in this case it's E. coli, and we call the fault region, which is the site type 0. We're defining that as extracellular.
And just for Winford, since he wasn't here, so like when he shows you the pictures, the subvolumes will be important. And he specifies those there, so it's going to be 32 nanometers and everything he's going to present on E. coli.
Yep. Okay, so with PyLM, we define the regions here with sim.app region, and we also are going to need the value of these site types. So sim.site types, this is a dictionary, and it associates the names we defined up here with the actual value of the element in the site type lattice. So we're going to define our lengths, 3.6 microns, 0.8 microns. Thickness is going to be a lattice spacing, and the width of the nucleoid region is going to be half the cell length. So the way that you construct things in PyLM is you use these geometric primitives. We have a point data type. I'm going to show you how to build a capsule using geometric primitives, but you can actually just call lm.capsid, I believe, to build a capsule on its own. But I think this will be more illuminating to see how it's actually done, how the sausage is made. So we're going to define the length of the cylinder, which I said before was L in that diagram. Simulation center, so that's going to be the centroid of the simulation volume. The center of the spherical caps, which is going to be along the diameter and at the ends, both ends of the sphere or cylinder. And we define these point objects here. So these are basically just 3 vectors, and those go into the calls to the cell builder in PyLM. So the way you build cells in PyLM is you think of it in terms of layers. You start from the bottom of the stack, and you keep adding layers until you're done. So this is the membrane, and we're then going to add a cytoplasm region on top of it, and then we're going to add the nucleoid region on top of the cytoplasm. So starting off with the membrane, we define a radius, and we build the 2 spheres. The LM sphere, P1 is the first spherical incap centroid. Give it the radius and the site type of the membrane. So this is the number here. This isn't the object. So this is, in this case, it's probably 1. Build the 2 spheres, and we build the cylinder. Cylinder takes the 2 endpoints of the cylinder, the radius, and the type that we want. So we do the same thing for the cytoplasm here, and we take the cell width and we subtract the membrane thickness. and this whole thing is divided by 2. So this is the radius minus how thick we want the membrane. That gives us the radius of the spheres and cylinders. Finally, if you do the same thing for the nucleoid region, this time we're using half of the width of the nucleoid for the radius, so that was defined earlier as half the radius of the cell. So we compose it. We start with the membrane. We add the spheres, the cylinders. We do the same for the cytoplasm, and then finally the same for the nucleoid. Now we can check our work and make sure we actually built it correctly. So this is how the visualization tool looks for PyLM. It gives us a widget here that we can trace through the site type lattice.
Nothing's happening.
Nothing is happening. That is correct. Reevaluate this. There we go. Okay, so the different site types are given over here. So this is external cytoplasm, membrane, nucleoid, and that's what we see here. We can then trace through it, and everything looks pretty much correct.
You had a warning in the previous slide. Order matters.
Yep.
And what, like, how you stack it up?
Yes.
Is that what you're saying?
Yeah, that's what I'm saying.
Oh, okay.
So if I go back to where I was defining this.
Yeah, there it is. Proposed.
So we start with the membrane first. So we add the membrane, and then we add the cytoplasm. If we were to add the cytoplasm first and then the cytoplasm would just blast over the membrane, and that site type wouldn't end up in the lattice.
Why?
Okay, so there is a subtle problem with the way that I constructed this. So the membrane proteins will be unable to explore the entire membrane. So there will be sections of the membrane that we constructed which are not connected by nearest neighbor diffusion. And just by looking at the output of the widget, that's not obvious. So in order to inspect that, we're going to use some image manipulation techniques. This is a labeling technique. So the idea is you have some sort of binary image, and you run this label function on it. What label does is it looks for all of the contiguous regions, and for each one of them it assigns a number. So for instance, if I have two squares, if I run label on it, it'll give me 2 different numbers. That's not what it was. But if you look at the output here, what I've done is I've called label. That gives me the number of labels. And that gives me an array of the same shape as the binary image, and it's integer valued. And each one of those contiguous regions has a different number. So I'm printing off the number of labels here. I'm printing off the value of the background. If you remember the image I showed in the upper left corner, that's black. I'm looking at the boxes, so I'm just giving it the indices of the box that I defined earlier, and I'm evaluating that at whatever the first index was. That gives me box label 1, which turns out to be 1. Likewise for 2, that gives me box label 2. So if I display it, you can see that this one got 1 number, and this one got the other number. So in lattice microbes, the way that diffusion occurs is it's hopping through nearest neighbor lattice sites. It's not hopping to second nearest neighbors. It can only go x plus 1 or y plus 1 or z plus 1. So we can use label to see if things are connected using that nearest neighbor connectivity. So I got these guys, they're like right on top, they're touching on a corner, but they're not contiguous. They have different values here. So if I run this on the membrane site type, so I get the site type lattice using sim.lattice, get lattice view. That returns the discretized lattice from PyLM. And I get a binary mask where the site type lattice is equal to the membrane. I run label on it, and there's 19 disjoint regions. So there's 19 different regions where particle types can't hop between. So if I plot it out, if I just plot a slice, this is a slice through the middle of the cell. You can see that this is completely disconnected, this is completely disconnected, but these sides are connected because you can like imagine like a circle right around a metal, everything should be connected that way. So how do we deal with this? Two ways: you can make the membrane larger, or you can make the lattice spacing finer. But there are cases where you need a specific membrane thickness, or you can't make the cell larger than you're already at the limits of what you can simulate in a reasonable amount of time, so you can't really make the fineness of the lattice lower. So the way that I came up to fix this is dealing with the site type lattice directly in JLM. Any questions on how to do this with Pylon? All right, let me switch over to JLM. So again, we're working with binary masks. So three-dimensional array, each element in the array is on or off. True means that that region is defined, or that point is within the region that we're interested in. And we construct the site type lattice by combining all of these disjoint site type or binary masks. So what's nice about this method is we can use set operations to build up the lattice, as well as these so-called morphological image processing techniques to sculpt the mask. So we can shrink stuff, we can make things bigger, we can fill holes, that sort of thing, and that gives us a lot of power over what the geometry of the cell ends up to be. So our standard imports are region builder, which I discussed yesterday, the RDB simulation, and the JLM style sheet, which gets loaded below. And we're going to be using a scipy.int image library, and that'll give us all of the morphological tools and things to shrink and contract the size of the lattice, that sort of thing. So we build the simulation object how we normally do. I'm printing out the size of the box because we define it in terms of lattice sites and the lattice spacing here. So it's 4 microns by about 1 micron in the other dimensions. So we define the regions very similar to PyLM. And we create a region builder object that we use to construct the site type lattice with. So this is going to be the same cell that we built before. This is going to be an E. coli cell. So these are the same measurements as before, constructing the half length of the cylinder and the 2 points. And we build the 2 spheres, sphere 1, sphere 2, and cylinder. And then we just take the union of those 3 elements to build the capsule. So these are just standard NumPy arrays right now. We're not doing anything with JLM, lattice micros, PyLM, or anything. So now we can take a look at the capsule to make sure that we did it correctly. This is a method available in the region builder object. We give it a capsule, and we can also say how big we want to scale the image that we see. So we can go ahead and trace through it, and it looks pretty good. Okay, we're going to repeat the same thing that we did for the nucleoid, but we're not going to do the membrane yet. The cytoplasm that we haven't defined the cytoplasm yet. We just defined 2 different capsules. So the cytoplasm is basically everywhere the nucleoid isn't right now. So we're going to take the union of the complement of the nucleoid, and that's just going to subtract it from the center. Finally, we're going to make the membrane, and this is going to be done by taking the capsule region we defined earlier and then growing it by a single lattice site over all of the directions. And then once we have this slightly larger capsule, we'll subtract the original capsule from it to get the boundary. So the way that we do this is using these morphological image processing techniques. So basic idea of this morphological image processing, or at least in terms of binary images, is you have some sort of probe, and this is like a smaller image. I'll get to that in a second. And this probe is traced across the image in all coordinates, all pixels of the image. And the way that it interacts with the image that's being probed defines a new image that you work with. So this probe shape is called the structuring element. So the most common morphological operations are erosions, dilations, and opening, closing. There's a handful of other ones as well, but these are the most useful to us right now. And we can define this using some set notation, but I think it's easier just to show you what these things do to images. So we're going to start off with a structuring element that connects nearest neighbors. So this is just its own image here. Yellow means it's on, black means it's off, and I put a point in the middle to indicate the origin. So this thing is going to be traced across the image, and the center here is going to be the center in the image, and that's going to be what we turn on or off in the output image. So I'm going to start off with an example here. We've got a square, triangle, a single point here. This is a single pixel, and this is a 3x3 box of pixels. So if we do a the dilation is defined to be, well, you can write it notationally as this with this O plus here with the image and the structuring element. But really all it means is we take that structuring element, that cross we started with, trace it over the image, and if any of the terms in the structuring element which are set to 1 touch any part of the binary image which is set to 1, the output image has 1 set at the center of that pixel. So what you end up with is if you have a structuring element that was just a single pixel, you get the same thing out. If you have a structuring element that has the next nearest or first nearest neighbors, whenever it's just 1 pixel away from the region, the true region in the image, you'll get an extra pixel there. So this is what happens. We start off with a small box, we end up with a big box. You can see that this is 2 pixels, and we gained a pixel over here. This single pixel turned into this 3x3 box. And I use the monster.
I think, this is really going into a great deal of detail.
This is
and
important.
I think, I know it's really important because I know the reason we gave the example of the PyLM is when we did the first min, CD, E simulations, we noticed the things weren't going to the ends somehow. We weren't, and it's like, oh my God, that move wasn't allowed. So then what we did is we went and we doubled the membrane everywhere. Well, that made the reactions take that much longer to do. So we go, that sucks. So let's come up with something better. And this is really much, much better. But if you think about it, like I was talking with somebody yesterday, like these terms like dilation and like that's almost like when is it with the Adobe Acrobat when you're trying to paint something there? So maybe we'll get to the point where we're dealing with cells. We can have these be buttons, but right now this is really how you have to interact with it. If you want to make that membrane thicker at one end or more pointy off at one position, you're going to have to know these commands to do it. And I think after a while, when we have enough really great examples, either we or perhaps Graham Johnson, who's sort of the lead visualizer at the Allen Institute, wants to help us with making these tools easier for people to use. Right? But right now, what he's showing you, this is really fantastic that you can dilate that thing out. This is exactly what we needed to do before. Right? Sorry, Tyler. Go ahead.
No problem. Okay. So yeah, I did have the wrong structuring element. So
good.
The point
Give
was.
you time to do it.
Yeah. Thank you. Yeah. So this is a single pixel, and you can see when we did the dilation, we actually got the same thing that we were using as the structuring element. So a single pixel turned into that structuring element. And that makes sense because if you think of this side right here, it'll only touch one side of the structuring element. Where if this is the second nearest neighbor, you have one of them right there and one of them right there, so it doesn't hit it. And if you look at this square here, you can see it bruised up around the boundaries, but it didn't hit the corners. So if you think of the cross right here, it's hitting what's outside of it, but it's not actually hitting what's inside the square. So let's try a different structuring element. This will include second nearest neighbors. So we have our first neighbors here, and we have our second neighbors here. So this time around, we do hit those corners that were missed. You can see the single pixel got translated to the same thing as the structuring element, and these both grown an entire connected boundary, or first nearest neighbor connected boundary. So the other method that we're going to use for building membranes is called erosion, and we use the O- notation here, and it's essentially the reverse. So if the structuring element hits any part of the background, it's black at that point or off. Otherwise, it's set to 1. So the structuring element has to hit everything in the region of interest. So you can see that when we apply the structuring element, this gets killed off completely. So that's gone, because if you put anything over this, it's going to hit some of the background. This kind of pulled off everything around it. So you can see these have all been reduced by a single lattice or a single pixel in all directions. So other operations which are useful are called opening and closing. Opening is done with the open circle, and it's an erosion followed by a dilation. And what happens is if you have a bunch of small pixels in your image, you can choose a structuring element that's a little bit bigger. And the first erosion will remove those, and then the dilation will then undo the erosion on things that are bigger. So that will have no effect on what the larger objects look like, but the smaller objects will get removed. So if you have experimental data that you've thresholded, so you have some sort of three-dimensional data and it's a scalar valued points like fluorescence or something, you've done a threshold on it, you're going to get a bunch of shaky noise in there. So you can use a structuring element that's smaller than the length scale of the noise and get rid of that and leave the big gross structures that you're interested in. The opposite is a closing, which is a dilation followed by an erosion. And this is good if you have holes in the image. So this will fill the holes and also connect things. Like if you have a couple of objects which are big, but they're kind of, they're disconnected but close together. The structuring element is of the same size as the distance between those two. Those will get merged into a single object. All right, so the whole point of this was how do we build the membrane? So the way that we build membranes with JLM is 2 ways. We can either build the membrane outside the region, or we can build the membrane outside or inside the region. So if we want it inside, we take the original object, so the capsule in this case, and then we do the subtraction, the set minus of the erosion. So we choose the structuring element depending on how thick we want it or what kind of like topological connectivity. And I'll show you what we typically use in the next slide. So inside or outside, for outside we'll take the dilation and then subtract the original object. Oh, whoops, sorry. Oh, what happened here?
You didn't run out of power, did you?
I plugged it in. Let's line up to.
You were there. The red. It just went blank on the red.
All right. So for instance, I have the new image in yellow and the old image are. I'm subtracting the two. So you can see that the inner boundary is 1 pixel. It has the same size as the original image, but we make the boundary inside 1, and likewise over here it's grown out. So nothing happened to the solitary pixel, but the little pixel got grown by a single lattice site here. So what's important is we use the second nearest neighbor structuring element here. So if you can imagine the first nearest neighbor, this would give us the cross, but instead we got the square. That's important because in lattice microbes, you can only hop nearest neighbors. So a particle within the boundary here can now hop all over the place. So JLM has a couple of routines built into it for doing these operations. So in this case, we're going to use region builder.dilate. We're going to give it the original capsule, and we're going to use a structuring element with the 26 neighbors, so the second nearest neighbors here. Run that and set it to dil_capsule. Take the original and take the intersection of the complement to get the membrane. And let's make sure that we actually have connectivity over the whole membrane. We do the label function, and it is the number of labels, and we get 1. So everything's good here. So for the extracellular is going to be it's going to be everywhere the membrane, the cytoplasm, and the nucleoid aren't. So since the dilated capsule includes the membrane in it, we'll just take the complement of the dilated capsule, and that gives us the extracellular region. Now we can compose the site type lattice. So these are the region objects that we already defined, and these are the site types, the binary lattices which define the different regions. So we compose them, and now we can take a look at what we made. And it is what we expected to see. Cool. JLM also has a 3-dimensional viewer, so we can take a look at the 3D construction in the notebook. This looks good. Take away the membrane, take away the nucleoid. Sorry, the cytoplasm, nucleoid. So, yep, that's what we wanted. Good, good. So that's it. That's JLM. Any questions on this so far? Yes.
Can I load in an image? Just basically, if I use something segmented and use this as the standard to the.
Absolutely. Yeah. In fact, that's what I'm going to talk about in like a couple minutes.
Actually, that, but hopefully we'll do his model pretty soon.
Yep.
Yeah.
Yep.
But one of the coolest things, we just didn't have time to show everything. We get the segmented data from the cryo-EM, and then he brings it to life to a cell. So if I can show you a slide of what it looks like when they see it, but they have already patterns that they sort of fill in, like a nuclear pore complex. They'll fill it in, and then they've done the segmentation, and then he brings it into the cell and builds up the entire cell.
Questions? Mike?
So at the end, you subtracted everything off to form that extracellular space. What would happen if we did something silly and ended up not labeling some part of the lattice as everything?
The API would complain. Oh. Yeah, you have to define every region, every sublattice, and you can't have multiple sublattices labeled or subvolumes. You can't have a subvolume labeled with multiple labels. So it will complain.
That's good, because when we got the first tomograph from work on Baumeister, we were putting them together,
Yeah.
and they left out a region in the middle, and we had particles flowing out of the cell.
Yeah.
It took us a while to figure out that there was a region not defined.
Yep. Yeah, one of the things that was really important to me when I built this interface was just checking my work, because I make mistakes sometimes.
No.
No. So it's good to have a computer check over your work. Any other questions? Yes?
So the combination with which you apply these operations, of course, involves trial and error and essentially learning. What I'm trying to get at is, do you have an AI engine that you want to talk to at some point?
Do I have an AI engine that I want to talk to?
Or do you want to employ somebody's AI engine for this?
That'd be cool. Yeah.
That's what I said. I mean, that's why we worked with the Paul Allen Institute. Their fellow, who's is a disciple of Good Cell. So they try to make things easier. And one of the things they're going to try to do is to accelerate the imaging analysis and assembly for us. But he'll make it somehow API that'll be much easier to use, but you have to have this functionality also make it clear, because we know what mistakes we made in the past, so we're trying to learn from it. And then also, as you move to eukaryotic system, as you saw, some of it looks like it's, well, is it really connected or not? You know, and those are decisions you might want to make on the fly. You know, most people think the ER should be totally connected, and making, with train stops at mitochondria and to the cell membrane and the nucleus, right? But exactly how you put that together, you need these kinds of tools to help you do that.
So, I mean, the way that JLM is set up, it consumes NumPy arrays. So that means you can easily hook PyTorch or TensorFlow into it with no, like, really any work. As far as I'm aware, those interact with NumPy really well. I haven't used them.
Yeah, just to follow up on his question, so there have been attempts to do it other ways, like there's a Blender, and I know you've had lots of experience with trying to set up things with Blender, but isn't that also going to have its problems? Very similar to PyLM?
Yeah, it will, because Blender cares about meshes, triangle meshes. It doesn't care about these volumetric data types that Lattice Microbes really ends up using in the end. So if you build something with Blender, you have to discretize that triangle mesh onto a lattice, and you end up with the same sorts of problems that you end up with when you try to do constructive solid geometry to build the lattice.
So we looked at that. So we sometimes make Blender movies of the final trajectories because they just look cool. It's and there's like Maya too. There's sort of various levels of making cool looking movies, and you'll also see we can use VMD, right? But I think our goal as scientists, we want to make it good enough that we can make our work understandable and demonstrate the physics and the chemistry of it. But improving it, that really needs to be in the hand of an artist like this Graham Johnson. Okay, crazy. This is really great.
Yeah, no problem. Any other questions on this sort of thing? Okay, now it's time for fun stuff. All right. Make sure I evaluate this. All right. So now I'm going to talk about how we can actually take real data and build a cell scale model of it. So your typical data sources for like three-dimensional imaging, it's going to come from cryo-electron tomography. You can get stuff from 2D microscopy as well, but you have to use a little bit of imagination to figure out what's going on in the Z direction. And then there's 3D optical microscopy. So there's confocal, which we heard about earlier. There's other super resolution techniques like STORM, 3D STORM, which will give you some idea of where particular fluorophores are around the cell. So you could label membrane proteins like PTSG and E. coli, which is a glucose transporter, and kind of get an idea of what the cell is going to look like. You could take the convex hull of those points to get an idea of it. And there's also other techniques such as structured illumination, which will give you some Z-stack information as well. So generally what you end up doing with JLM and Lattice Microbes in general for using this sort of data is you got to do some pre-processing first. This isn't something that JLM will do. So you're going to have some sort of set of data where you have each point in space defined with a number or a set of numbers, like fluorescence intensity or the density you would get from electron microscopy. And you're going to have to figure out some way to mask off each region. So you're going to have to say that this thing is the nucleus, this thing over here is mitochondria. That sort of estimate is going to need to be done. And once you've done this, you're going to have a binary mask for each region. Now that you have the binary mask, you have to process that into something that Lattice Microbes can consume. In that case, you have to change you have to change dimensions. You have to rebend your data so it actually fills the simulation volume. if your segmentation is done in a really kind of sloppy way, like I would do if I had fluorescence data with like thresholding or something like that, you'd have noise, and you'd need to remove that noise somehow, either by filtering the original data, low pass filtering it or something, or taking the segmentation and then doing like closing on it or opening rather to get the points removed. You can also end up with overlapping regions. So when I look at the cell-free data or the label-free data, we'll see some of the regions overlap, and we'll have to figure out what to do with those points. And then once you've gotten segments that you're happy with, you need to figure out the other stuff, like membranes or other, or the compartments, like cytoplasm, extracellular regions. And if you have some features that are smaller than the resolution of the imaging, like nuclear pores, you'll need to add those as well. Yep, I had talked about that. All right, so I'm going to take the label-free data, and I sold this off the website. If you guys haven't been here yet, definitely need to go play with this. It is really awesome. It's 3D visualization, so you can move it around and see all the cool stuff. So the data that I'm going to work with has been pre-segmented, so I don't have to do any of the hard stuff. It's confocal data, so we have a pixel size where the Z direction is a little bit larger than the X and Y directions, and this is the bioarchive link to the machine learning algorithm techniques that they use to actually do the segmentation. So here are our standard imports. I'm using H5Py because I've already saved all the data into an HDF5 file. I'm going to use IPython widgets to look at the data. And here is SciPy in DImage, which is necessary for all of the image processing stuff. So I'm loading my data as an HDF5 file, and we'll be able to treat this as a dictionary and access all of the different data sets within it. And I'm going to visualize the data that we have so far. So this is just IPython widgets. It's a decorator that repeatedly calls this function with different parameters based on how I set these controls here. So I'm going to set the gray level to the bright field, and now we can look at the different channels. We have a lot of stuff here. Let's just look at...
What's ACTB_free?
That is beta-actin, and that's going to be the actin filaments or microfibrils or whatever they are. So you can kind of scan over it and see where all that's ending up. Let me show you the actual cell membrane.
So that's their bright field image. That oh my God, great.
So they've already segmented everything for us. So I'll show you the nucleus this way. This one. Nope, that is the. Here we go. You can see the nucleus, and Sec61B is the endoplasmic reticulum. So yeah, that's the kind of data we have. So I'm only going to work with a subset of it to deal with the actin, which are calling microfilaments. The cell membrane is cell. It's the convex hull. It's not convex hull, but it's the filled-in cell. DNA, I'm just going to assume that the labeled DNA is the nucleus. We have the nucleolus labeled, we have the ER labeled, mitochondria, and microtubules. So I'm going to load all this data into a dictionary, and I'm renaming these things because I can't always remember what Tom 21 means. So everything gets its own name that labels the compartment.
That's when physicists do this.
Yeah. Well,
You could relate. Okay.
Okay. So the first thing we want to do is crop the data, because if you remember, there's a lot of blank space around the cell. So I'm going to use a labeling technique. So I take the union of all the regions that we're looking at, just in case some of it falls out of the membrane, take the union of all that, use measurements.findObjects, which is similar to the label function I showed you earlier, and then I use this findObjects gives us a list of slices into the array, into the binary array, so we can pick off the start and end of each slice, and we're going to give us a buffer of 1 pixel on each side. And now we use a dictionary expression here to just process everything in place. So I take the original segmented dictionary, iterate it over keys and values, and then I slice it. Question so far? This is going to be kind of advanced Python-ish, so if anything doesn't make sense, just Okay, now we have to choose the lattice spacing and the total size of the lattice. So there are trade-offs involved with how we decide. So if we make the lattice spacing too small, we're going to waste memory. And if the lattice spacing is really small, it's going to be on the order of molecules, and it no longer makes physical sense. So we have to have lattice subvolumes which are significantly larger than the size of the molecules, but we don't want them so big that we completely lose all the spatial behavior we're interested in. So if you choose a fine lattice spacing, your simulation time is going to be a lot slower because you'll have to take finer time steps. So what we're going to do here is something about, I think I used 110 nanometers for the lattice spacing, and that's just so I can get away with removing single subvolumes to create the nuclear pores later on. So in lattice microbes, the dimension of the lattice, there's the actual limit is a little bit more complicated than just 32. I think it's 8 on X, Y, and 32 on the Z. But we're just going to make it all a multiple of 32 in each direction. So our lattice spacing is 115 nanometers. And we're going to scale and So now we're going to take the measurements that we're interested in. So the pixel size, we read out of the HDF5 file. And the shape of the array, we just look at PER. It doesn't matter. They're all the same shape. And now we can compute what the required lattice size would be given the lattice spacing that we've already defined and the pixel size. So in order to take this data, which has uneven dimensions, so the Z direction is longer than the X and Y directions, we're going to end up with a lattice shape that is going to have more, it's going to span, you're going to have subvolumes which span over multiple, you're going to have subvolumes which include data from multiple Z pixels. So the lattice spacing is 0.15, 115, and here are our lattice sizes. So they're kind of big lattices. Now to import the data, we're going to use the scipy image.zoom to unevenly scale the data to take into account the uneven Z measurement. And at the same time, we're also going to deal with the 32 nanometer or 32 subvolume. Actually, yeah, we're going to deal with the 32 subvolume lattice boundary condition that we need, and we're going to also pad it. So the exact details aren't super important. Something similar to this will be in the advanced tutorial later on. So again, I'm going to replace the segmented data by iterating over all of them and just calling this process function up here. Are we good so far? Okay. So there is a problem, and I alluded to this earlier. Some of the segmented regions overlap. So I'm going to prove this to you by this little chunk of code here. I am iterating over all combinations of the site lattices of the data, the binary segmentation data, and I'm taking the intersection of them and counting them. The count is greater than 1, and I'm not trying to compare against the nucleus or the cell. I'm going to print it off. So the majority of things overlap at least a little bit. And since I said earlier, a subvolume can only have a single single lattice type or site type, we need to correct the overlaps. So the trick that I'm going to use is another image processing technique, and it's called the distance transform. So we're going to use this distance transform to decide where to split the regions up. So consider another two-dimensional image. We have two squares, and they overlap in the middle. I want to figure out some sort of intelligent way to make these two squares into two disjoint regions, or not disjoint regions, but two separate regions. So consider the first square. I'm going to take the distance transform of it. And what the distance transform does is for each pixel within that region, it assigns a number, which is the distance to the boundary. So the guy in the center has a distance of, yes, 10-ish? Doesn't sound right, but okay. It's a number that tells you how far it is to the boundary. So if I take one distance transformed subregion and take the other distance transformed subregion and subtract them, we end up with a segment down the middle where that actually separates the two regions out evenly. So it turns out that this trick here is easily extended to 3 dimensions. But now that we have this, we can separate these guys really easily by just saying, I want the positive ones, and I want it to be inside the object. So that gives us this region here. Then it's I want the negative ones, and also in that object. So that gives us 2 binary regions, and then we can combine them as necessary later on.
But, you know, when you were going through your original data that you said, you know, they gave you segmented data, and you were showing the nucleus, and then you showed the ER. I don't know if you just unfortunately chose the same color, but it already looked there like the ER and the nuclear membrane were overlapping. Is that also in the data, or I have a feeling what you're doing now is correcting a bit because of the resolution that have now made things. But what about when they send data to you?
Actually contact?
Yeah, were they making actual contact, or was there at least a little bit of space between them?
It's that's us.
Okay.
Don't worry.
Yeah.
We'll be right back. All right.
Just
I would not be surprised that they overlap because just of the resolution of the light microscopy.
well, that's what I'm thinking too. So I think even when they're doing segmentation, and you know, when you talk to people, people say it's like the ER comes and sort of gets even into the nuclear membrane. So if you want that,
So
like,
what you have to do in that circumstance is use your biological intuition. If you think that those are connected, then you can make them connected using whatever techniques are at your disposal.
and then just allow transitions from a site type that's like I'm in the nuclear membrane into the ER.
Yep.
And you would have to allow that. Okay.
Yeah.
But like you say, it could be that it comes out through the segmentation that way, or you've introduced it because of the resolution that we use for the simulations.
Sure. Like I'm going through this in like kind of a cookbooky manner, but you can't do that. You have to understand the biology behind it, or otherwise you're just making pretty pictures. Which is nice, I guess, but not science. Okay. So going back to the stem cell, yeah, this technique generalizes to 3D. So this method of using the distance transform is just one of a million different ways that you can come up with to resolve the ambiguity. This is the easiest, I think. So, well, it's not the easiest. You could just blast one over the other, but this is the fair kind of segmentation, I guess. So do the distance transform of both of them, compute the distance, and then take the intersection of the positive and the original, and the negative and the original, and return a tuple. So I give us 2 images, gives me 2 images out. So now I iterate over all combinations, separate them, and change them in place. And after we've done this, I then check for overlapping ones. So what I've done here is just did like a union of all the pairs, and going to check the overlappiness. None of them overlap. We're good for now. Let's go on. Now we need to construct the membranes and the other space. So we're going to use the same techniques that I showed earlier with erosions and dilations and other set operations to build this stuff. So the membranes, we're going to use second nearest neighbors. And for the plasma membrane, we're going to grow it. And for the nuclear membrane, we're going to shrink it. So for the plasma membrane, I'm taking the binary dilation of the cell segmentation data, and I'm subtracting the original from it. So that'll grow it by a single lattice space, and it will be contiguous. So if I put proteins in the membrane, they'll be able to explore the entire membrane. So just making sure here, I label it and count, and we have one region. So we haven't done
Why is
anything
that number
weird.
0?
Huh?
Why is that 0?
It's counting the number of regions, the total number.
Oh, okay.
Yeah. So it's the background. It's actually 2 regions. It's the background and the first labeled region. Okay. So for the nuclear membrane, we're going to subtract the dilation, subtract the erosion from itself, so that the membrane doesn't overlap with anything else. So starting with the nucleus, subtracting the binary erosion of the nucleus with a second nearest neighbor structuring element.
But the labeling for these regions you have borrowed from elsewhere, right?
The labeling came from the
their
analysis
data.
models. Yes.
It's whatever the image analysis that came from Paul Allen Institute that they decided.
Yeah, even if they gave us some sort of set of fluorescence images for everything in there, it would still be really difficult to deal with. You could do it, but it would make my already very long notebook way too long. So I'm very happy that we have the segmentation. Okay, so now we're going to take, there's a little bit of overlap between, so there's a little bit of overlap between the nuclear membrane and the plasma membrane. So we're going to fix that overlap with this statement here. And now we're going to exclude any of the segmented regions like the mitochondria, the ER, all that sort of thing, which are outside the cell. Some of them can be based on however the segmentation ended up. So we're going to take a mask, which is the nucleus and outside the nucleus, and we're going to subtract that from everything. We're also going to mask off the nucleolus so that none of that is actually seeping out of the nucleus as well. And finally, we'll construct the cytoplasm, the nucleoplasm, and the extracellular regions just using the standard techniques that we've done before. All right, so now we need to add nuclear pores, and I'm going to choose 2,000 of them. Not completely arbitrarily, I have put a BioNumbers session number here, so if you don't believe me, you can check it out.
But these are not visible in the data from
No.
Allen.
Yeah, no.
So you cannot see the nuclear pore complex.
Yes, you can't see them, and I have no idea how they're distributed. In fact, the algorithm I'm going to do to distribute them will put them in a way that's probably not realistic, but it's enough for the demonstration. So one thing that's slightly important is we don't want the pores to overlap or be directly adjacent, because instead of having a single subvolume as the aperture in which things can come through, you're going to have 2 subvolumes. It's going to be larger and it's going to be less realistic. So we need to take that into account. And the way we do that, so we just do a for loop, and we keep track using a set of all of the pores that we added. And we use a first nearest neighbor structuring element to test. Actually, no, I'm not doing that right now. My mistake. I was doing another method earlier where you were going to check that the pore actually did something. So the pore actually connected the nucleus to the cytoplasm. I'm not doing that right now. It was a lot of code. This is already a lot of code. So basically what we do is we just loop over it, and we test to see if we've already added that pore. or if that pore is near any other pores. And if it isn't, we add it. If it is, we keep going. We throw it away and keep going. So now we can build a region for the nuclear pores that we do iteratively as we go on, and we subtract the pores from the membrane. So our membrane actually has the pores in it now. Okay, another implementation detail of lattice microbes is you generally want the long axis to be along the z direction. So I'm going to transpose everything here, and now we have it along the long axis, or along the z-axis. Finally, we get to check our work. Okay, that's the best part. Oh, yeah, never mind. But yeah, first we check if they're overlapping, then we make sure that everything is defined. And one thing I also wanted to do here is see how, yeah, let me actually show this slide. So one thing that was kind of important for me to check is you have all these things in the cytoplasm. And you want to make sure that these objects you place in the cytoplasm actually don't completely cut off the rest of the cell. So to do that, I labeled a region in the cell. The way I constructed that region is I just came up with open space, which is going to be the complement of everything that's not open space. So then I label that region that I came up with, and I pick off the region in the center. So that region in the center is going to be some weird thing that is connected, that has all the open space connected to it. So I label that, I compute how many subvolumes are in that connected region, and then I compute the number of subvolumes in the union of all the other open regions. Does that make sense?
Or just checking the connectedness
Yeah, it's just
of your final cell.
Yeah, that's all it is. And it's 99.8% connected, so I'm not really concerned about those other subvolumes that you can't get to. Those are obstructions as far as I'm concerned at this point. All right, now the fun part. We can look at the lattice. So I have an extracellular region here. I'm going to remove, and here's the cell. There's that antenna I asked about earlier. Let's turn off the open regions in the nucleoplasm and cytoplasm. Let's peel it open. There's the plasma membrane gone. And we can see all of the different structures in here. So one thing you may have noticed is I just kind of blindly included all of the regions in the segmentation data. In reality, something like these microtubules, they're not going to be that big. They're going to be a collection of much finer structures. So you would want to come up with some sort of more intelligent way of constructing the microtubules based on the segmentation data.
Can you turn off the microfilaments and the microtubules?
Yeah,
So
I
you can
know.
just see the mitochondria?
I'm working on it.
Sorry.
So here are the mitochondria in the teal. Mitochondria are not beans. I learned that a couple of months ago when I visited out. Yeah.
Oh, and they're the holes in your nucleus.
Yep, there are the pores. I'll get
Okay.
there in a second. And in orange is the ER. Get rid of that. Get rid of the tubules, or mitochondria rather. And I'll get rid of the pores. Oh, I can kind of see that. So one thing you may have noticed, let me turn on nucleoplasm. The pores will. Oh. So you'll see that, actually no, there's a better way to show the pores. Okay, so the distribution of the pores is kind of, well actually I think it's uniform here. I used a different technique earlier and they weren't uniform. But it looks okay. So let me show the nucleolus, with the nucleolus inside. Yeah. So all
And
done.
so the number of the nuclear pores that you took from the literature, that reference that you gave,
Yep.
there's roughly, for these stem cells, should be about
I don't think it was a stem cell. I think it was just a generic mammalian cell.
Generic. Okay. So,
But I mean, I'm sure that's probably accurate for the stem cells. Accurate for whatever so. Okay. Do we want to look at this anymore? Are we good for now? Okay. I would kind of feel bad about not at least running some reactions in this model I built. So I came up with a really boring reaction model. Hopefully, in the future, I will have a less boring one. So we're going to do a simple model. It's just going to be your standard biomolecular association reaction. So set up a simulation using what we always do. Now we're going to build the cell using the region builder compose. Now we're going to add diffusing species. I'm just going to add some A into the nucleus, add some B into the cytoplasm, and those will go to C. So the reaction is just going to be association, and it's going to be diffusion limited. So 10 to the 9 is the rate constant. The reaction is A plus B goes to C. The rate constant of A. This can only happen in the cytoplasm. We're going to set up the diffusion behavior, and another caveat here is I'm taking all of the regions as hard obstructions. That makes no sense because of things like filaments, other sorts of regions in the cell. You're going to have particles which can diffuse through those. There might be a different diffusion coefficient, but they're not hard. But for this demonstration, it's okay. So we're going to set all the transition rates to 0 initially, and then set up the diffusion model for A. A starts in the nucleus. It can come out of the nuclear pores, but you will notice that there isn't nuclear pores to nucleoplasm here, so it gets transported out through the pores, but it can't come back in. And we set up diffusion in the cytoplasm. B will stay in the cytoplasm, and it won't interact with anything else. And C, for some arbitrary reason, I chose it to be able to enter the mitochondria.
Susan will have
Yeah. All right, so we're done with the model. Write it to disk. Run the simulation. So you can call the solver, or you can just run LM in a bash cell. Now we can load the file back up and look at the particle numbers as a function of time. So I've got A's, B's, and C's. So I'm looking at A's in the nucleus, A's in the cytoplasm, B in the cytoplasm, C in the mitochondria, and C in the cytoplasm. So yeah, it looks like we are dropping a lot of A in the nucleus, and then A in the cytoplasm starts to build up as it leaves the nucleus, and then it starts to interact with B's and it starts to die down. And C is in the red, so you start to make a lot of C, but it ends up in the cytoplasm.
You don't see much fluctuation. You don't see much fluctuation.
Yeah.
Is that just because of the number?
It is the number. There's no decay.
Mm-hmm.
So
Okay.
the steps, if you were to zoom in, you would see individual steps here, but they're monotonically increasing. All right. So DMD. Let's see. So I loaded this up in DMD. This is actually a different simulation. It's the same model, but I did the nuclear force different, which is why it looks like there's a chunk missing.
Are you running that on your machine, or you were running it on the cloud?
I don't have enough memory on this machine to run it, so this is on the cloud.
Okay.
Actually, it's not the memory. There's a technical reason why it's not working, but I know.
So that's all up and running on the VMD on the cloud?
Yes. All right. So start turning stuff on. Here's our site type lattice. Okay, so I'm going to turn on plasma membrane.
That's pretty.
Yes, there we go. Now we can see inside the cell. Turn on the RDB particles. breaks through. So we have a lot of A in the nucleus and a lot of B outside. You can see it, how it's kind of separated. Now we can scan through the trajectory, see the mix, and eventually they all start to coalesce. And that's when they're finding their way into the mitochondria and not coming out.
And what are the mitochondria in it? That's the green?
It just chose random numbers, so,
Uh-huh.
or random colors.
Okay.
How long does it take to run such a simulation?
This simulation is over a very short time period, so it finished up in like, I guess like 15 minutes. I ran a much longer simulation, which was over an hour, and that took a better part of the day.
And then, what GPU were you running this on?
This was on a Titan V.
So that's, you gotta have a really, but you have pretty good GPUs there, but I don't know if you have the Titan Vs there. Yeah. Like,
So yeah, you can kind of see how they're ending up in the mitochondria. Any questions on this? I'm about done.
so just a comment, what would really help in the next layer of imaging, we don't know where the genes are really located. You can go in, maybe label one, and then we can follow that gene as it's being it's being turned on. But if you can think about any way that one can start imaging some of the chromosomes, that would be fantastic. And maybe not even the entire chromosome. I think it would be enough to have certain genes, particularly for those that are involved in some of these differentiation pathways. It'd be good to see when they come on, and then look for correlations in it. Right?